Considering the rapid warming that's happening in the polar circle in the north, there are reasons why the Antarctic is not as uniformly and as rapidly warming as the Arctic polar circle. But nonetheless, it's of great interest to see when the seasonal sea ice may disappear in the Arctic. There have been incidences of, the sea ice disappearing enough that people could go from the Atlantic into the Pacific, so-called northwest route, and so on. But theoretically, you would want to know when it was that the last time Arctic was really seasonally ice-free, and this nice paper does that. There are a lot of technical details on how they do that, what kind of paleoproxies they use to derive the seasonality of such things. It's not very easy, but there are ways to do it, and this brave group does that. A seasonally ice-free Arctic Ocean during the last interglacial. It turns out that they can infer that maybe the last interglacial was seasonally ice-free in the Arctic. The extent and seasonality of Arctic sea ice during the last interglacial, so about 129,000 years to 115,000 years before present, and then we started getting into the last ice age. This is poorly known. Sediment-based reconstructions have suggested extensive ice cover in summer, while climate model outputs indicate year-round conditions in the Arctic Ocean ranging from ice-free to fully ice-covered. So people take models, coarse resolution models, because they have to be run for a long time, and they have sea ice models, and they take solar forcing from that time, but you don't have all the information you need in terms of land use, etc. But despite all those limitations, they can give you useful information, but they say that maybe the entire year was ice-free, but maybe summer was ice-free. Okay? Climate model outputs do that. Here we use microfossil records from across the central Arctic Ocean to show that sea ice extent was substantially reduced and summers were probably ice-free. This is critical. They are doing good work, but they are also humble in admitting the uncertainties. The evidence comes from high abundances of the subpolar planktic foraminifera, turboral. These are biological names are not easy, forgive me. Turborotalita kinkeloba. You think I should practice that before recording, but I read it, then I don't realize I cannot fully pronounce it, and then I start recording. Nonetheless, the evidence comes from high abundances of the subpolar planktonic foraminifera, Turborotolita kinkeloba, in 5 newly analyzed cores. So these are new analysis of the cores. The northern occurrences of this species is incompatible with perennial sea ice, which would be associated with a thick, low salinity surface water. So they are using the habitats of where this occurs, T. kinkeloba occurs today. We assume a uniformitarian principle and say similar dynamics would have worked in the past, and say that it can only grow when there is a thick, low salinity surface water, so freshwater layer, to make them bloom in the Arctic region. Instead, T. kinkeloba's ecological preference implies largely ice-free surface waters with seasonally elevated levels of primary productivity. In the modern ocean, this species thrives in the Fram Strait, Barents Sea, Arctic, the Atlantic Gateways region. So Fram Strait, Barents Sea, Arctic, Atlantic Gateways region, implying that the necessary Atlantic Ocean sourced water masses shoaled towards the surface during the last interglacial. This process reflects the ongoing Atlantification of the Arctic Ocean, currently restricted to the Eurasian basin. So Atlantification of the Arctic Ocean is basically bringing enough Atlantic water and heat and creating ice-free conditions where you have Atlantic water mass properties, which is the Atlantification, which is presumably what would have driven this bloom during the last interglacial. This process reflects the ongoing Atlantification of the Arctic Ocean, currently restricted to the Eurasian Basin. Our results established the last interglacial as a prime analog for studying a seasonally ice-free Arctic Ocean expected to occur this century. So it's good to have past climate information which can be used as analog to where we may be headed to understand what are the processes that would drive us towards that past analog and what it would mean for the overall global warming emissions and so on. So here is the region, study area and the core sites. You can see the bunch of core sites here. These are the sediment cores which are from before, ice cores here, and overview of marine sediment cores and ice cores mentioned in the text together with the bathymetric map of the Arctic Ocean. So you can see the bathymetric map here, deepest regions occurring here in the dark blue regions and shallower regions occurring in the lighter blue colors. Okay. Mean ice edge positioning during September, January and January for 1981 to 2010 are shown here in these white contours. Yellow circles indicate core sites in new microfossil data. White circles indicate sites with microfossil data that is used in the data compilation, so they used data extracted before. White squares indicate sites used for comparison with stratigraphic and geochemical data. These sites either have no planktic assemblage data from more than 63 micrometer fraction, which corresponds to various data paleoproxies you can extract, or calcareous microfossils are not well preserved. Gray circles are ice core sites. Modern pathways of Atlantic derived ocean currents indicated with red arrows here. And okay, so you have the splits into Barents Sea, North Atlantic current going, this is the Fram Strait, the East Greenland current here, and the various pieces of the currents in the Arctic itself. Tells you why this is almost like a closed water body with fresh waters and can freeze easily to form sea ice much thicker than anywhere else you will find on the open ocean. There's a reason why sea ice doesn't get very thick, but I won't get into that here. Okay. The modern pathways of the Atlantic derived ocean currents is indicated with red arrows. The color transparency change signifies subduction of Atlantic waters beneath the 100 to 200 meter thick Arctic halocline. So these are under the ice in the current configuration. Norwegian Atlantic current here, West Spitsbergen current here, and let's just read them for completeness. East Greenland current I mentioned, Central Arctic Ocean, Fram Strait, Barents Sea, East Siberian Sea up here, Laptev Sea down here as LS, and we have the ice edge defined as locations with a 50% probability of ice occurring at a concentration of 15% or greater. This is a figure adapted from somewhere. So here is the time period. I skipped the proxies they used, and just looking at the longer time scales going back to about 270,000 years or so, you can see the various marine isotope stages, which I have covered in some detail in my course on climate and human evolution in terms of climate simulations for these periods. But the zoom in of this last interglacial is basically the MIS 5, so we were talking about 129,000 to 115,000 years or so. So this is where the previous ice age ended. You came out of it, you had an interglacial like we are in now. Of course, we are accelerating the warming with greenhouse gas emissions and so on. Data compilation and interpretation. So sea ice minimum, sea ice maximum from summer and winter of 2020, and where T. Kinkeloba and no T. Kinkeloba locations are cited to make sure that If they occurred during the last interglacial, that means most likely there was a fresh, thick layer of ice-free waters to allow them to grow. Okay, so here is the sea ice minimum during the summer and where the T. Kinkeloba have been located in the newly analyzed cores. Okay, compilation of new and existing T. Kinkeloba occurrences with greater than 1% of the seafloor assemblages to ascertain significance of the occurrence. During modern times and last interglacial, together with the observed and reconstructed sea ice conditions, with bathymetric map in the background. Modern T. Kinkeloba occurrences and sea covered here, data from published databases combined with the results from this study. Sea ice extent is from the National Center for Sea Ice, National Sea Ice Data Center, I think. T. Kinkeloba occurrences and sea ice coverage during LIG. Extent of the LIG summer minimum sea ice extent is inferred on the basis of our new T. Kinkeloba constraints, assuming this species requires large ice-free summers. This is a maximal estimate for summer sea ice minimum, since there are currently no observations from sediment cores north of the Canadian Arctic archipelago region that comprise the last interglacial sediments. Okay, so all said and done, we seem to have some evidence that there was significant occurrence of T. Kinkeloba during the last interglacial. So you have to find them, you have to date the time of their finding, and then interpret their occurrence as ice-free waters. Conceptually, illustrative model depicting ocean stratification and sea ice conditions in the upper 500 meters in the modern Nordic Sea Arctic Ocean region. In A, that's what we are looking at. Their hypothesized transformation during the last interglacial shown here. The transect is located along 5 degree east meridian from 70 degree north to the North Pole. So you can try to locate yourself. 5 degree east would be somewhere here, and you are going at 70 degree north to the North Pole. Sorry. Okay. The occurrences of T. Kinkeloba and N. pachyderma in the water columns determined from plankton toes in the modern case, inferred from sediments from LIG case, are indicated with small black and white circles respectively. The relative abundances at the seafloor, summarized from the existing and new data presented here, are indicated by the pie charts. So here you are going from 70 north to the pole, along 5 degree east, just east of the Greenwich meridian. Here you have open waters, and here you have the Fram Strait sea ice cover, Central Arctic Ocean with perennial sea ice cover. So this is the modern time, and you have basically another species occurring here, which is the N. pachyderma, with the T. Kinkeloba occurring here, and you can see the occurrence is much higher here, begins to decrease as you get here, and basically disappears under sea ice. Whereas if you go to the last interglacial, looking down to 500 meters, the abundance of the T. Kinkeloba is still lower in the complete open waters, but partially ice covered, potentially seasonally uncovered, seasonally ice-free waters, the abundance is higher. So here you have the Arctic water and the Atlantic water in both cases. So now you have more Antarctic water. During the last interglacial, of course, there was Atlanticization of the Arctic, so Atlantic water was larger, and now we are presumably heading in a similar direction of bringing in more and more subducted Atlantic water into the Arctic and warming the Arctic and creating ice-free conditions. So it's likely we will have ice-free conditions. Of course, the implications are that even if we didn't have greenhouse warming, if we continued into the interglacial, presumably we could end up with seasonally ice-free Arctic, but that is something we do not want to claim, because people will again say, haha, see, we didn't do it. But the Arctic warming and polar amplification are directly attributable to human activities and increased greenhouse gases. So we are at least accelerating the Atlanticization of the Arctic and arrival of the seasonal ice-free regions in the Arctic. Okay, in the context, so reading a bit at the end, in the context of rapidly decreasing sea ice, an important goal of paleoclimate studies is to identify the last time the Arctic became ice-free. The invasion of the Arctic basin by Tikinkaloba provides the first firm evidence for extensive seasonally ice-free conditions across the interior Arctic Ocean, where perennial sea ice remains in place today. Therefore, we put the last interglacial forward as the youngest and perhaps the most relevant geological period for studying a seasonally ice-free Arctic Ocean, which is expected to occur this century. This almost looks like a poster child in terms of actual impacts of global warming, and maybe one of those so-called tipping points, which is not a terminology I like so much, just because it's being used to make heuristic arguments about how close we are to them and when they may occur, and so on and so forth. This information provides a useful constraint that can be included in ocean and climate models, leading to an improved understanding of Arctic sea ice in the climate system. Okay, I thought this is a nice little paper that I should include as a new finding. Even though it's a paleoclimate study, it has direct bearing on global warming and our future. Okay.